All right, so today we're going to go through the quantum mechanical postulates. Last time we did the messy math of the spectroscopy. So we started at a spectrum, went all the way down to the wave function. And we found the wave function on the horizontal axis of the spectrum. That's where the peaks are. And the wave function tells us where those peaks are. It's the differences between the different waves, the energy of those waves. And so that tells us where the transitions are. Think of that word transition. It means something's changing. So we're changing from if it's absorption, a lower state to an upper state. If it's emission, we're going from an upper state to a lower state. So there's a transition occurring, and that has an energy difference. So we have energy levels, and the difference between those levels gives us the spectral lines, the peaks in the spectrum. So that's all about the horizontal axis. The vertical axis also has the wave functions. Okay, and so that's the transition dipole moment integral. That's not this lecture, that'll be the next one. Okay, so this one is about the wave function. So we're going to look at the quantum mechanical postulates today. So what is a postulate? Well, it could be used as a verb. You could postulate something. You could suggest that something exists, right? And it would be as the basis for reasoning, or the actual thing that's assumed to be true would be called a postulate. So the existence of a wave function is a postulate. We can't prove it. We can't get down and see them. Okay, we can barely see atoms. Okay, but if we postulate their existence, the math works out and we can simulate the spectrum, and we see that the simulated spectrum matches what we see in real life, and so then we have confidence in our postulates. But postulates are a starting point. So if you don't understand how the world can be described as waves, that's okay. We're assuming that's true and seeing how the math works out. Does that make sense? So that's why people say, if you try to understand quantum mechanics, you never will. It's because you start with certain assumptions that can't be proven. So once you start with an assumption that can't be proven, there's nothing below that. Okay. So don't be so freaked out by it. Everybody's so freaked out, but it's just the physicists say, shut up and calculate. Right? Don't now, but I'm not satisfied by that, because I'd like to think about metaphysical things. I was like, what is the wave function? Could we understand that? Does it really exist? Is the whole universe just a bunch of wavy strings that don't ever dampen out? You pluck a guitar string, eventually it gets quiet again. It dampens. These wave functions go on forever. So we don't have any understanding of how that could be. Aristotle called it he said all nature is in motion. The wind, you see the leaves on the trees, you see the water moving around. He said there has to be an unmoved mover. What got it going? If you come into the room and you see the dominoes falling, and they're falling and falling, don't you want to kind of look back and see where the first domino was? That's what Aristotle was saying. What was the unmoved mover that started it all? Well, if we have wave functions, then that Aristotle question is still in play. What started them all? So those are the metaphysical. Those are the metaphysics behind it. And you don't need to get into the metaphysics to do the calculations. And so that's why the physicists are always saying, just shut up and calculate. But if you're metaphysical curious like me, then I like to think about those things. Okay, so this lecture covers those postulates that are the foundation or basis for quantum mechanics. So postulate number 1 is about the wave function. So it's saying the state of a mechanical system is completely specified by the wave function. And then it also has some pieces that fall from that. The square of that wave function is going to be the probability distribution. So we'll explore what that means with a few examples. Okay, but you can think about that. If you think of the wave function, you've got positive and negative regions. If you square it, the negative regions become positive. So wherever there's a lobe in the wave function, that's deemed now the probability of, if it were a particle, where that particle would be. So if you had a spoon small enough to scoop out the particles, there wouldn't be where the wave function is 0, there would be where the wave function is non-zero. And then we can integrate this over all space. If you look everywhere, then you're guaranteed to find the particle. What's the probability of a guaranteed thing? 1. If you multiply it by 100%, it's 100, it's 100%. If you integrate over all space to find the particle, you should get 1. So that requires our wave functions be normalized. We can come up with just a function like a sine function, but it's not going to be normalized. So we're going to have some constant out front that makes this integral equal 1. Now, because again, we didn't do multivariable calculus in your degree plan, we're going to have a hard time with a quadruple integral. So we're going to just focus on the particle in a box problem with just one dimension. And so our overall space is going to be the x-axis from one side of the box to the other. So we're looking over all space, which in our case goes, if it's our box length is 10, we go from -5 to +5. And so that's all space. We can do that kind of integral pretty easily. So we're only concerned with this one dimension. Now there are invalid wave functions. If we want to have, let's just go with this bottom one first. If the area under the curve has to equal 1, then the curve can't go to infinity, right? Because it would have an infinite area. So this is not going to be a valid wave function. We need to be able to do a sum all the way across. And if you're right here, what is the value of the wave function? Well, there's three answers. So we can't have any wave functions that double back on themselves like that. In the Schrodinger equation, we have a second derivative operator. So we have to take the second derivative. So we can't have any wave functions that have sharp points like this. Okay. And then we can't have any broken wave functions. They need to be continuous. Okay, so we can't have any of those kind of broken, disjointed places in our wave functions. They need to be smooth and continuous, and their first derivative needs to be continuous. So these are the four criteria that allow us to get that probability distribution by squaring the wave function. So let's build the wave function for the particle in a box. In the last lecture, I just gave it to you. So let's see where that came from. So we know that sine functions, cosine functions, those are waves. Those are things that would be suitable for wave function, options for a wave function. And so let's say our box length is 7 on the x-axis. If we put sine 7 on there, notice it goes through one full period of the wave function. You know, it hits here at 3.14, that's pi. It hits here back to 0 at 2 pi. And so if our box length was 2 pi, it'd be perfect, but it's not, it's 7, okay? And so we've got a problem here. It's finite between 0 and L, that's fine. It doesn't go to infinity anywhere. It's continuous. It has a continuous first derivative. There's no sharp points on it, but it's not 0 at the boundary. And so we need to figure out a way to address this. And so what if we divided x by L? So if we divided x by L, then from the left side, x is 0. From the right side, x is L. And so this goes to 1. Well, the sine of 1 is not going to be 0. Okay? But if we multiply that by pi, then when x goes to L, we get 1 times pi. Okay? And so then that gives us this first lobe of the wave function. So this is a great wave function. It's finite between 0 and L. It's continuous. It's got a continuous first derivative, and it's 0 at the boundaries. So that's the criterion that de Broglie, the fellow that thought about these waves in the first place, he said standing waves are 0 at their boundaries and they oscillate. So this wave function could oscillate. But it's not centered on 0. Now that's one of my things that I like. I like my wave functions to be centered on 0 so that we can see the symmetry of them. We'll understand symmetry in the next part of the course. But let's go ahead and slide this wave function to the left, half of the box length. And the way to do that is to put a phase factor inside these parentheses. So inside the parenthesis, instead of x starting at 0, we want it to start at the far left, or L/2. Okay. So we're going to scoot it left by pi over 2, and now it's centered on 0. So it's finite, continuous, first derivative's good, 0 at the boundaries, and now it's centered on 0. But it doesn't have any quantum numbers. So this can't explain any excited states. And so where do we put the quantum numbers? Well, we want it to get higher and higher in frequency. So we want it to go up and down more. So that's got to go inside the sign. So quantum numbers can't be out front, they got to go inside. And so we can put some quantum numbers in there. And now we have an oscillating wave function that has excited states. So we put the quantum numbers in here. And now we can see the first three excited states. Okay, so it's finite, it's continuous, zero, it's centered on zero, zero at the boundaries, and now it has quantum numbers. Okay, but it's not normalized. But at least we have wave functions. So, can I get you to help me out? So this is what we've got. So this is n equals 1. Just hold it still, I'll do the oscillating. So this is n equals 1. Okay, see how low energy it is? It's just barely moving. And then this is n equals 2. There we go. See, it's much faster. So that's n equals 2. It'll be harder to get n equals 3, but I'm going to tell me when I get it. I think that's n equals 4, isn't it? Okay, slow down. There we go. Yeah, that's n equals 3. You see how I had to go a lot faster to get n equals 4. Let's try. And you could probably measure the frequency and they would be all nice whole numbers of, there's n equals 4. Now it starts to kind of spin, and that's what's happening in time dependence. So it's spinning in and out of the imaginary plane. So the time dimension you could think of as coming in and out of the board in terms of I and negative I. So I don't know if you remember your imaginary numbers and those kinds of things, but Euler's relationship, you have sine minus I cosine and so on. So you have real, plus 1 real, then plus I, then minus 1 real, and then minus I. So it's spinning like this. So this would be the time dependent with the imaginary plane going in and out. It'd be like a jump rope, like that. And so what we're always looking at is just the real plane. So you don't have to worry about what happens to the wave function when it passes through 0, because it's not gone, it's in the imaginary plane. And so that's what's going on. So whenever you're a jump rope now, you're going to think of n equals 1. It'd be fun to see two people do the jump rope on n equals 2. That'd be neat. That'd be a good TikTok video. So let's see if I can do 5. Did I get it? Hold it up. Is that 5? Count the nodes. There should be 4 nodes. 6. See, it's not a standing wave, so I don't know what's going on there. What's that one? Ah, okay, I can't get higher than 5. All right, thank you. So that's what we see with these, they're standing waves, right? Even though my hand was shaking, once I got it into the standing wave, I didn't have to do much. Like it already had momentum and I could just hold it there, very little movement on my part. But it's not normalized. So let's look at the normalization thing. So all our wave functions have a maximum of 1 and a minimum of 1. If that wave function has a spot that's already 1, the area under the curve can't equal 1. The area under the curve, if I squared it, would be greater than 1. If once you square it, whatever spot is 1 is just still going to be 1. Okay, and the pieces less than 1 will shrink, but they won't go to 0. And so by definition, if any spot on the wave function is already 1, then the integral over all space of that wave function squared is going to be greater than 1. And we don't want that. We want it to be normalized. So we're going to have to shrink this thing down a little bit by a normalization constant that will, once everything's squared, will cause the area under that squared curve to be 1. So let's do a little bit of calculus. This is a review. This is I don't like to skip steps because I was not strong in calculus when I was in school. And so I was looking at it, I was like, okay, why are you skipping steps on me? So I'll walk you through this. We'll go pretty quick, but it'll be on video. And so you can go back and kind of see what we did. So we showed the waves with this linking. So what we're doing is we're going to square the wave function, integrate over all space, and set it equal to 1. And then we're going to solve for this constant that we put out front. Okay. There's some terminology associated with orthogonality and normality. So if we took the wave function times some other wave function and integrated over all space, the integral result would be 0. And so only the wave function times itself should give 1. And so this is just a vocabulary term, this Kronecker delta, this little delta n prime n, that is 1 when n prime equals n and 0 when n prime equals n. It's just, again, a piece of vocabulary. Looking at this in matrix form, which we'll see in Excel, is that anytime a wave function is multiplied by some other wave function and integrated over all space, you get 0. So all the off-diagonal elements are 0, but anytime a wave function is multiplied by itself and integrated over all space, the result is 1. So let's do this. Normalization of the 1D particle in a box. So here's our function. Now, one of the criteria here that we need when we've got signs multiplied by each other, first of all, we can pull these ends out. So these are constants. These are normalization constants, so they'll come out front of the integral. And then because the stuff inside the parentheses on sine are identical, we can combine that and have sine squared. Okay, so we've got sine squared, and we pulled that capital N, that's our normalization constant, that we're going to use to force this integral to be 1. So we set it equal to 1 and solve for n squared after we do the calculus. Now, I don't have my sine squareds and stuff memorized, but I've got my integrals and derivatives of sine and cosine memorized. Okay, so let's just go through that quickly. So let's take the derivative of sine x is what? You're right, cosine x. And then the derivative of that is minus sine. And then the derivative of that is minus cosine. And so then it goes back over. The derivative of minus cosine is back to positive sine. So these are the 4. This is the way it goes. If we're doing integrals, it goes up. So the integral of sine is minus cosine. So we're going up. Okay, so, but we can't do that on sine squared. So we look up a trigonometric substitution. So what we're trying to do is we're trying to get rid of this square. So I don't know if you remember your calculus, but a lot of times the professor would use these substitutions and I wouldn't know why they were doing them. Okay, the only reason we're doing them is to reduce the power of our sine. So we're just getting rid of sine squared and getting to something that we have memorized, which is cosine. Now this is actually 2, this will break it into 2 integrals. This 2 will go in front of underneath the 1, and it'll also go underneath the cosine. So this is what we end up with. We end up with 2 integrals. We're going to have the integral of 1/2 and the integral of the cosine piece. We can actually pull those 1/2s out front. And so we have the n squared over 2 times the integral of 1 times dx. That's the easiest integral you'll ever do. The integral of dx is x. Okay, and then we have this integral of the cosine. So we've done the integration. So we've taken the integral of dx and we've gotten x. So that's this piece right here. And then we've taken the integral of cosine here. And so we go up 1 step, and that gives us sine. Okay, so this negative sign out front does not change. So we went from cosine to sine, and all of this stuff stays put, but everything in front of the x comes out, and in an integral it gets flipped upside down. Because if we were to do the derivative, it would come out without being flipped, and it would cancel everything. So when we do the integral, we bring this stuff out front, but we bring it out upside down. So that's the L over 2 pi. And then we already had a 2 here, so 2 and the 2 gives us the 4. So everybody sees that, no skip steps. Okay. Now we evaluate it. This is a definite integral, so we have limits. And so we have the L over 2 and minus L over 2. So here we put those pieces into that first result. That's this one. So we evaluate it at L over 2, and then we subtract the lower limit. This is where people miss a negative typically, is they forget to subtract it since they see that negative sign already. But those negative signs cancel each other, and then we've got that. Now let's do the sine piece. So we evaluate it. So wherever there's an x, we put an L over 2 or a minus L over 2. And then it's already negative, and so when we take the difference, we have a positive here. So let's look at this. Where our 2's cancel, the L's cancel, and we've got n pi plus n pi. So we've got 2n pi on this piece. You see that right there. And then over here, our 2 cancels, our L cancels. And then we've got n pi minus n pi. So this is all 0. And so we got the sign of 0. Now, this is where your knowledge of the trigonometric functions come into play. We've already seen this. We saw the sine function go up and down and up and down and so on. Every integer multiple of pi. So we can conclude from our knowledge of sine functions that every time there's an integer multiple of pi, sine evaluates to 0. So that's what we've got here. We've got our quantum numbers are integers. And so we have integer multiples of pi inside the parentheses. So every one of those sign pieces is 0. And so we have 0 minus 0, so 0. But that's just for this second piece of the integral here. So all of this stuff goes away, and we're left with the n squared L over 4 piece. So we can simplify that to n squared L over 2. Okay, it's like we have a fourth plus a fourth, that equals a half. And then we solve for that n squared. So n is the square root of 2 over L. Yes? Because we have this n pi here, and we have this plus another n pi. Thanks, that's a good question. Yeah. So yeah, the 2's cancel, but then we have 2 of those pieces that add together. So now, this is the factor that we put in front of the wave function. See, it goes right up here. So if that factor were right here where n is, then when we do this square and we integrate over all space, our result is going to be 1. So we figured out what that piece in front needs to be. So this is our normalized wave function. Notice now it no longer goes all the way up to 1. It goes up to square root of 2 over L. So that's what we've done. We've normalized our wave functions. And then here's with the slinky, you saw all of these. These wave functions have been multiplied. No, let's see. The energy of these wave functions has been added to all the values so that they're offset. But they're not in nature not offset. They're all just on the axis oscillating. But it helps to picture them offset by their energies. So if we square those wave functions, the shaded area, if we integrate that shaded area, it will equal 1. That's if we look over all space. But what if we look in the first 10% of the box? So if we just integrate this piece right here, if it was classical, like if we had a marble in a box, there would be an equal probable possibility that it could be anywhere in the box. And so in the first 10% of the box, it would be 10% probability, 0.1. But we integrate this and we see that it's not 0.1. For the ground state, it's quite a bit. It's like 0.01 or 0.05. And whenever you get a result that's not sort of the classical result, that's a quantum result. That's the quantum features of this box are showing up of this system. And here, for n equals 2, it's still quite a bit lower. And for n equals 3, it's lower. But notice what happens when you go up in quantum number. So this is n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 20, and then 30, and then 40, and then 50. What are they? It looks like they're converging on a number, doesn't it? What is the number? The 0.1. So we're integrating 10% of the box, and eventually we get this classical result that 10% of the time the particle is in that first 10% of the box. Okay. And so this is some principle that we see in quantum mechanics, that as you go up in quantum number, it approaches the classical behavior. Okay. So that's That's sort of a principle that you can see. Also, there's really no hard transition to a quantum realm. Notice the quantum effects kind of oscillate and grow in stronger and stronger as you get closer to the ground state. Let's prove that the wave functions are orthogonal to each other. So here we have the n primes and n. They're not the same number. So n is not equal to n prime. I'm going to go fast through this one because we'll run out of time if I don't. But this one is not able to be combined into sine squared because the things inside the parentheses are different. So we can't do that. So we're going to end up with this. We're going to go ahead and pull that square root of 2 over L out front, and since it's two of them times each other, the square root goes away, and we end up with 2 over L out front. And then we have this n prime and n, and we do have a trigonometric substitution. We end up with the sum of cosines. So this piece, you have the n prime piece minus the n piece, and the n prime piece plus the n piece. So the arguments inside the sines get combined, and we now have 2 cosines. We now have 2 integrals, which we can do. So we pull out, let's see, what are we pulling now? Oh, yeah, the trig substitution also had a 1/2 in front of that, and so we lost the 2. That's where the 2 went. So we break this into the 2 integrals. We've kind of recombined everything so that we get everything that's a function of x, like here's x, here's x. So we combine everything on x, and so we have this difference between n prime and n in front of those, that one, and then the sum in front of x on this one. We do the integral, we have the definite limits of L over 2 minus L over 2, and when we did the integral, the piece in front of the x came out front and was inverted. Now where'd the L go? Well, we had a 1 over L here when we brought it out, and it canceled out. Same thing on this one. And so now let's evaluate these things. So here we have, again, if the integers, if quantum numbers are integers, then the difference between integers is an integer, and the sum of integers is integers. So once again, we have the integer multiples of pi being 0. So all of these pieces go to 0, and there's no other integral in this piece. So we don't have the integral of dx in this one because we didn't have the sine squared. And so now everything goes to 0, so our wave functions are orthogonal. Any wave function times any other wave function is going to be 0. So you're not going to get any sort of spontaneous transitions from one wave function to another because they don't talk to each other. That's another way to think of orthogonality, is there's no way for the wave functions to talk to each other. You saw how hard it was for me to get from one wave function to another. I had to add quite a bit of energy. Well, energy in our situation is light. Light has to come in and cause the transition from one wave function to another. I can't just be sitting there waving along and all of a sudden see wave function number 2 appear. Something has to happen. I have to give it more energy, and then it can appear. But I'm interfering with the system. So if you don't interfere with the system, you don't get any quantum jumping, and you don't get any light in or out. Okay, so now we get to observables. So these energies that we've talked about, they're observable. At least the differences are observable. And so this is a postulate. Again, this is something that we can't prove, but this is what we observe, and so we're going to postulate that every measurable property has a corresponding operator in quantum mechanics. So we can now simulate experiments in the lab by using the operators and the wave functions. So that's what we're doing in this course. Here are the operators, but we're mostly focused on this one, the Hamiltonian operator, because this gives us the energy. So the total energy, kinetic plus potential energy, is the Hamiltonian operator, and it involves that second derivative of the wave function. So it's how curvy the wave function is. You saw with the slinky that the ground state wave function was not very curvy, very smooth. The slope doesn't change very much. But then as we got to the excited states, there was lots of curves, and it went through 0 a whole bunch of times. So you can count the number of nodes to know how curvy or how much energy the wave function has. So this is telling us the energy is related to the curvature of the wave function. So this measurement of an observable is using these eigenvalue equations, and so we'll solve one of those in a second. Okay. And it's the properties of the wave function and the operator and the boundary conditions that cause the system to be quantized, to have these standing waves. So let's look at the Schrodinger equation. So here's the Schrodinger equation where we operate on the wave function with the operator and we get the observable, which is the energy. Can I get you to close that door? Someone? Thanks. So let's put all our pieces in. So we have the Hamiltonian operator from the previous page. Our potential energy is 0. So this is H. And a lot of times they put a hat on there just to indicate it's not a constant, that it's actually an operator, it's doing something. Then we have the wave function here, psi of n. And then we end up with this constant that comes out, E, and then the wave function psi of n. So notice we operate on the function and we get it back. So we need a suitable function, which we know sine is a suitable function for the second derivative operator, because once we do the second derivative, we get sine back, but a -1 has come out front. And so without any of these other constants, our energy would just be -1. It's the thing that comes out front. Okay, but we've got L in there. We've got the mass of the particle is part of the Hamiltonian. We've got Planck's constant, 2 pi, and all these different things. So those are going to be involved in our energies too. So we just ignore the right side of the equation and we just do the operator. So we take the second derivative and see what happens. So we do we do the derivative one time. This n, pi, and L come out front and they're inverted. And then sine becomes cosine. It doesn't change the sign out front because it's positive sine goes to positive cosine. So we haven't changed our sign yet. But we still got one more derivative to go. So we do it again, and this time, going from cosine, we end up with minus sine. And so now our negative out front is gone. We bring the n pi over L out front and invert it. And so now we have that squared. So we had the sine, cosine, and then minus sine, and minus cosine. And this is sort of the derivative, so d by dx. So as we do the derivative of sine, we get cosine, and then when we do cosine, we get minus sine. So that's where so here we went from cosine to minus sine, and that's where the went away. Okay. And we got our wave function back. We have no more derivatives, no more integrals, nothing in there that we have to do. So now it's just algebra. So we've done the calculus, we finished with the algebra. So we, by inspection, see that the energy must be equal to everything out front. Now we know that h bar is h over 2 pi, and it's h bar squared, so this is squared. Okay, and so then we have a pi squared over here and a pi squared over here in the denominator, so the pi's are gone. But then we have a 2 squared, which is equal to 4, and it's multiplied by that 2. So this is going to give us an 8 in the denominator. So a lot of times people see that 2m, and in the bottom, the next thing they see is 8m, and they're like, where the heck did that 8 come from? Well, it was inside h bar. Okay, so, and then we have L squared, we have h squared, and then we have n squared, the quantum number. So this is the analytical solution of the Schrodinger equation for the 1D particle in a box energies. Not every quantum system has an analytical solution. Okay, so let's list the ones that have analytical solutions. We have the particle in a box, which is what we're doing. You could put this wave functions on a ring and talk about rotational motion, and that's in the book chapters that I have posted on Blackboard. You do the particle in a box, and then there's a little side thing where we do the particle in a ring. That's a one-dimensional system. It has analytical solutions. They can do particle on a plane or on a disk or in a sphere. And so the hydrogen orbitals, 1s, 2s, 2p, all of those have analytical solutions. Okay, so all hydrogenic systems have analytical solutions, meaning we can sit down with pencil and paper and our knowledge of calculus and solve the Schrodinger equation. But when you get to 2 electrons, we don't have analytical solutions. So that's a little strange. It's disappointing. You know, you get to helium and we can't solve it. Okay? It's because the electrons are acting as standing waves, and all of our calculus is really particle based. I mean, we're doing wave calculus here too, but as far as the location of electron 1 and calculating the Coulombic repulsion for electron 2, we need an R12. And how do you do R12 for that Coulombic repulsion term when your electrons are smeared over the whole ball of the atom? So it's disappointing, but we have approximate solutions for the helium on up. Okay, and that's why we get into computational chemistry and Gaussian calculations for our real molecules. Now, the expectation values are just the Schrodinger equation in a different form, or similar kinds of equations. And so how did we get this? Well, if we had H psi equals E psi, and we left multiplied by the wave function, technically the complex conjugate of that wave function, which we haven't talked about, and we integrate over all space, both of those. The E is a constant, and so it comes out front. And so then we have this. And then you can take this piece over here and move it over to the denominator. And that's how we end up with this equation here. So this is just showing, you know, for some property A, we have that A operator operating on the wave function. If we left multiply by the complex conjugate of the wave function and integrate over all space, that's another way to solve for that property. So it's essentially the Schrodinger. If we're talking about energy, it's the Schrodinger equation. If we're talking about momentum, it's some other kind of equation. So I just show you that we get the energy one when we have this. So this is another way to specify those energies, is this expectation value terminology. So when the quantum number here, so this is N and N, we end up with the energy for that wave function, or for that particular quantum state. And if we're taking differences, this energy difference between those quantum states would be E2 minus E1. So you can see, you know, if we were to do the math, this is the equation that we would solve, which is pretty ugly. But we have the analytical solutions for the particle in a 1D box anyway, so we can just plug those in here. But I'm just showing you where the wave functions are in all of this mess. So let's solve for this transition energy, frequency, and wavelength. So here we have the transition equation for all possible transitions. So we're going from N to N prime. Let's say it's, in this case, it's absorption. So we have N and N prime. And notice the little star that says homework on it. Okay. So this difference here is delta N. And so that's how we're changing. So we can do this for all possible transitions by just putting delta N in here. Now notice the h squared and 8ml squared, all those things are constants. So we'll just pull them out front. And then we have all of the quantum number changes here. So this is a little algebra problem. You know, remember FOIL, first, outside, inside, last. We've got this thing in plus delta N squared. And so we'll do that. This is the FOIL piece right here. So we end up with N squared. We have the 2 times delta N times N, and then we have the delta N squared. And then we have minus N squared, which came down from this piece right here. Well, that's nice because the minus N squared and the plus N squared cancel, and we end up with this piece that survives. Now what I did was I pulled the delta N out front just because this is a very common way to write these, some quantum number plus a half So we'll look at this this equation here as the general equation for the change in energy for a quantum transition. So if we're jumping by one level, we could put delta n equals 1. If we're jumping by 3 levels, we could put delta n equals 3. And so we can calculate any of the transition equations. What is the transition equation? It tells us where the peaks will be in the horizontal axis. So maybe we're taking an experiment and everything is on the x-axis of the spectrum is in frequency. Well, this is it in frequency. So delta E is equal to h nu. So nu is equal to delta E over h. And you can see we've lost we've lost the square. So we've divided h squared by h, and we end up with this equation. What about wavelength? Well, we have delta E. We have nu here. I'm going to test you with my little joke. What's nu? C over lambda. Yeah, say it louder. What's nu? Okay, good. So we have equals hc over lambda. So therefore, if I wanted to solve for lambda, I move the delta E underneath. So lambda is equal to hc over delta E. So now delta E is upside down. It's down here in the bottom. Notice that my ends and everything went down 1 over that. And I had the h squared in the bottom. I'm multiplying by hc, so my square is gone. I have a c here. And so basically I've inverted delta E and multiplied by hc. So this is my wavelength. So if I have a spectrum, I'm going to have these peaks here. And this would be the 1 to 2 transition. This would be the 2 to 3 transition, the 3 to 4 transition. So this equation tells me where my transitions will be in wavelength. So we're dealing with the horizontal axis, the differences in energies. Okay, so those are my general transition equations for all possible transitions. And then the 5th postulate is time dependence. So the evolution of that wave function in time is given by the time-dependent wave function, which is our regular wave function times e to the it. So the imaginary number times time. And so it's an oscillatory piece that goes in and out of the complex plane. But we're not going to deal with time dependence. The most time dependence we're going to do is what I just demonstrated with the spinning jump rope type wave functions. It's complicated enough. Okay. Is everybody okay with that? See some nods. Okay. So we've gone quick enough now that we have some time for questions. So what about this? I mean, step back. Like, it's a lot of math and everything. If you have questions about what's the point, that's okay. Ask that. Yes.
How are we going to be expected to apply this?
Yes. So part of this, there's a piece that's appreciation. Okay. This is pretty complicated and it's just one dimension. Imagine radius and angle, longitude and latitude for the hydrogen atom. Now we have 3 different variables and we have waves associated with all 3. It gets super complicated, okay? So part of it is an appreciation of the difficulty of doing it by hand, because when we get to symmetry, all of this can be done on a Post-it note. Yeah, so then you have an appreciation for why symmetry is so valuable. Okay, go through the chapter. You've seen how detailed I did today's couple of calculus problems. The one in the chapter 4, I think it is 3 or 4, as we go through the intensity equation, which we're going to do in the next lecture, is 4 to 6 pages. I can't remember. I think it's like 6 pages of calculus. Okay, and that's just in one dimension. And if you could reduce 6 pages to a Post-it note, that's a good thing, right? So that's when we see symmetry really play a role. Okay. Now, you don't have to know every little deal, but you do need to know things that are reviewed from calculus. Like if you get the result of an integral, and I typically put this on the exam. We did this analysis, we get this result right here. Come on. There we go. We get to this point right here, we evaluate it, and we get this. And you don't have this little zero piece here. So I give you all of this equal sign and nothing. Like tell me what this equals. And you don't have this little bracket, 0, bracket, 0, bracket, 0. You need to remember that the sign of integer multiples of pi is 0. Okay? Because you can do the calculus and get here and still be lost. This is the piece that requires thinking. I know that's insulting to people who struggle with calculus, but calculus is procedural. But this last piece really isn't procedural. This last piece requires you to think about it. And that's what I want to test you on the exam. Like when you get the result, you're still not there. You still don't know what it equals. Okay? And so when we get to the intensity equations, we end up with cosines here. Well, cosine oscillates from +1 to -1, and so it requires a little bit more thinking. Like what situations? Well, maybe when our quantum numbers are odd, we get one result. When our quantum numbers are even, we get a different result because they're -1. Maybe some things cancel, maybe some things don't. And so that's the thinking piece. So that's where I would want you to apply this piece. I think it honors our requirement for you to have calculus before you get to this course, because wouldn't it piss you off if you like were delayed in your degree plan trying to get through calculus and then you come to PChem and we never used it? Yeah. So the part of using it is knowing how to do it, but also knowing how to appreciate that it's just waves interacting with each other. And if I'm going to do math on waves, I'm going to need calculus. I'm going to need to know how they change, which is derivatives. And I need to know with this postulate number 1, if I square the wave function, that's the probability distribution. So I need to do an integral over all space. So that's where the integrals come in. As applying this directly, in the second part of the course, we're going to do it numerically. So all these derivatives and integrals we're going to do in Excel, which is super easy. Because what's the derivative? It's the slope. What's the slope? Rise over run. So I just take the y-axis difference and the x-axis difference and put that in a new column and copy that formula down. So I'll teach you how to do calculus in Excel, and you won't care about memorizing what sine to minus cosine is, because Excel will figure that out for you. It's beautiful. So again, you'll really appreciate that too when we get to it. Great. Have a great day.